Welcome to the course on thermodynamics and propulsion. This is a course aimed at second year undergraduate students at IIT Bombay. We will start with an introduction to the subject where we talk about thermodynamics, what it is, and what aspects of it we will be focusing on. We will also talk about propulsion or the engineering side of things, of engines, especially aircraft engines, and how thermodynamics connects to propulsion and how propulsion gives back, in turn, connects to thermodynamics. So let us begin. Thermodynamics, when we say, at least from our high school days, what comes to our mind is pressure, temperature, volume of a gas. We know how they're related, we know how to calculate them and how to work with these quantities. Now, all of these quantities essentially are related to the energy of the gas, and thermodynamics is nothing but study of the energy of a gas, liquid, any material. In fact, a more complete definition of thermodynamics says that it's a study of energy conversion. How to convert one form of energy into another. We all know about kinetic energy, potential energy, internal energy, and many other forms. How do you convert one to another? Or more importantly, how do you convert energy stored in a material, whether it is a gas or any material, into mechanical work? This is really important for us. Energy stored is to be converted into mechanical work, and that's what engines do. And this mechanical work in the form of force can be used to drive machines. As engineers, or budding engineers, we are all interested in machines, in engines, and how they work, how to make them work better. In fact, the beginning of thermodynamics goes back to the steam engine. And a steam engine precisely did this. It had hot steam generated by boiling water, and how did they make that steam to drive a machine, drive a piston, and the piston was connected to something that was pulling water from deep below underground mines and so on, and it was driving railway engines and so on. Now, when we talk about these energy conversion, they happen in certain devices. There can be many different kind of things. Like if you are boiling water in a kettle, it's actually converting heat into steam, for example. So it's the simplest example, and there can be many more. So we will write this term called energy conversion devices, which are essentially devices or contraptions which do the job of thermodynamics for us. And what is inside these energy conversion devices? What is really storing the energy and what is really doing the work is called working fluid. Fluid is generally used to refer liquids and gases. Not in all such scenarios what the material inside the device will be liquid or gas. It can be solid. So it essentially it's a general term used for what is happening inside and what is the energy stored in as the working fluid. When it is pressure, when it is liquid or gas, it's easy to see that the pressure, temperature, and volume are the properties of the gas that really help us calculate the energy stored and see how much of it can be converted into something useful. And that's where comes the laws of thermodynamics. These laws are framed in a way that they help us to quantify how much energy there is. They help us to calculate how it can be converted, how much of it can be converted, how much cannot be converted into useful work. All of these come from laws of thermodynamics. So quantify the properties and the energy. Okay, now let's take a look at a few examples. There are many, many examples, but let's take some of the few major categories of examples in thermodynamics, or the devices that do energy conversion. The first and the most important for us are engines. They can be the engines that is under the hood of your car. It's an internal combustion engine known as IC engine. It's other important engine for us is those on aircrafts. We'll come to know that they're called gas turbine engines. They're called turbojet engines and many other variants. Steam engines, as we mentioned earlier, any form of engine. What they do is they take the chemical energy in a fuel and then somehow convert it into mechanical work. They may be rotating a shaft which is connected to the wheels. They may be generating a high-speed jet which propels the aircraft forward, and so on and so forth. Other category which is quite closely related to engines is power generation. Much of power generation now happens from coal. They can be nuclear power plants, or you can go back to the traditional hydraulic power plants. Now, hydraulic power plants, we have water at very high height, where we look at the potential energy of the water, and then that is taken to drive a turbine, and that gets converted into finally electrical energy. That is fed to our homes for our usage. Another common category of thermodynamic devices are appliances that we see in day-to-day life at our homes. Take a steam iron. It takes electrical energy and converts it into heating. An air conditioner takes electrical energy to cool a room. Refrigerator, another very common example in thermodynamics. Microwave oven, maybe. All of these are appliances which actually are converting energy and somehow managing energy to make it something somewhat useful to us. We'll come across many of these examples as we move on into the course. An example which we do not come across very commonly is supersonic or actually hypersonic flow of, for example, air. This is again very important, especially important for aerospace engineers. If you have a flow which is at a very high speed, it has a lot of kinetic energy. If you're sitting on an aircraft and it's flying supersonic, fighter aircraft, the air that's coming towards you is supersonic. That high kinetic energy gets converted into heat, and that heat is right next to your aircraft. In fact, if you're sitting in space shuttle, the heat is too much to bear, and you have to really put those protective tiles so that heat doesn't leak into your cabin and burn you up. The opposite thing happens is in a rocket nozzle. You generate a very high energy gas and then pass it through a nozzle to generate a very high speed jet. So heat gets converted back to kinetic energy, and that high speed jet gives you the thrust force that lifts up the huge rocket up into space. The last category that we'll mention, although there are many more, is those examples of energy conversion that occur in nature. One of the common examples, and it's quite important in the current scenario, is weather, where we have cloud and rain. These are not so-called devices, but these are systems in which thermodynamics plays a major role. Human body is another example you can think of, where different forms of energy are getting used in different ways. Astronomical situations, astrophysical situations like black holes, and so on. Many of these have energy conversion going on. So the list goes on and on. But let us move to the next point that we want to make for all these examples, is that thermodynamics is all pervasive. By that I mean thermodynamic principle, thermodynamics, energy conversion is everywhere. It's all around you, starting from the small kettle of boiling water, making tea, electric kettle, to the rocket engines, from stars to human body. Everywhere there is thermodynamics. So now, if you want to, so that makes it very important. It's actually really a fundamental subject. If you know thermodynamics well, you actually can start analyzing anything around you. It's also a bit tricky, because you want to make laws which are applicable to each and everything. The same laws applies to everything. So the laws have to be very general. And they have to be framed in a way that they don't specifically meet only one of the examples, but every example. So what happens generally in traditional study of thermodynamics is that we define the laws in terms of a very general shape, a very abstract form. We take, which I called a potato-shaped body, and potatoes can come in very different shapes. It can fit into, or think of a balloon or something of that sort, a shapeless thing. And then we say there can be heat, there can be work, there is energy, there is a system, there is a surrounding, and I'm sure you have come across these things before. Now, once we go a little further, we have enthalpy, entropy, all this. And I call these, some of these, as very abstract concepts, because when we talk about energy, fine, energy relates to temperature and heat. So we can feel it in some ways. But what about enthalpy? Can you say this is enthalpy? Can you physically get a feel of enthalpy? It is difficult. Even more difficult is entropy. We define it as a disorder of atoms and molecules, but really we can't see it. In the level of where we can see and feel and measure something, what is entropy? So see, some of these are quite abstract concepts. And that is what I feel is one of the challenges in thermodynamics, to study and understand and use abstract concepts. What we will do is take a slightly different approach. We will study thermodynamics, at the same time study engines and understand thermodynamics from the point of view of engines, perspective. From the engine perspective, we will understand and study and learn thermodynamics. Everything starting from system to work to heat, everything will be given. We will start from the engines, how it works, and then say, yes, if you understand for IC engine, maybe you can understand for the next engine, and then you can generalize to anything. But the strong fundamentals, the groundwork is based more on the physical picture and not on an abstract subject. I will soon introduce some physical examples of engines, and we'll see how it works. Examples, of course, will include piston, cylinder, which is something I'm sure you have seen before. You will see how a compressor works, how a turbine works, how an aircraft engine works. So these are real examples that will help us. Compressor, turbine, etc. will help us. These examples, these machines, real machines, will help us learn thermodynamics. And so this I call a physical approach compared to an abstract approach. And we will take the physical approach in this course. And what I aim to do by doing this physical approach is to develop what I call as intuitive understanding of the subject, where once you look at it, you don't need the mathematics will follow later, but once you look at a problem, you'll pretty much understand intuitively what's going on, what is heat work, what are the losses, and what is the energy, and then comes entropy, enthalpy, to quantify those and do calculations to get answers.